Chapter 6 is what we're going to be focusing on here with this slide. And what we have up this session is air pressure and winds. When we consider air pressure and winds, what we need to answer are some fundamental questions about our atmosphere, such as why do we have air pressure and where are winds from? So those of you that go into engineering, you will certainly deal with air pressure and the flow of those pressure coefficients, and then eventually work on those pressures in regards to either a liquid, like in a hydraulic situation. And those of you that go into education, even at the elementary level or middle or secondary level, you're definitely going to be working with winds. Why does our planet have winds? What are their relationship to these? And certainly it affects all of us because we can recall a windy environment, and we are close enough to those tornadic sequences where most of us can probably remember a time where we were at a loss of some personal or property damage because of wind or storms or rain or the mix of those. So let's dive right into this. Winds and air pressure. What we see in this chapter exemplified at the beginning is a simple reason for why we have wind. It's just the difference in air pressure. We have a horizontal difference. Remember, think advection here, a horizontal motion. And what we have is a horizontal pressure difference across the Earth's surface. And the reason we have those differences is because of the difference of surface coverings. We have water, we have land, and then we have different types of terrestrial material that are a mix of vegetation or soil or sand or rock or whatever the case may be. They all have different types of heat capacities. They all have different types of albetics that roll into those mixes, and that creates different micro pressures. And regionally or locally, they can produce different types of winds. And those pressures create a net sum that then can drive wind from one area to the other across the planet. And as we look at the certain types of zones of winds on the planet, we can certainly make an association to why that takes place. And that's the overarching goal of this chapter. Atmospheric pressure is the force exerted by collisions of gas molecules. We did a good connection to this, hopefully at the beginning of the course, and we should have a composite view of what atmospheric pressure is in general. But now we're going to get to a little bit of greater detail as to why does that pressure change? What does that mean when the pressure changes atmospherically? How does that affect us? Some of us have certain types of members within our family, or maybe you, where you've had an injury before, and you can certainly tell when we have a change that's occurring in the atmosphere. You might have an elbow or a knee or a leg or maybe a wrist that's been badly broken in the past, and you've got some scar tissue in there, and unfortunately it will swell. And those are things that we typically notice most of the time in our major joints of our body. So if you have somebody that's arthritic in your family, or maybe you, if you've had some repair work done to a knee or to an elbow or to a shoulder because of a bad injury or an accident in the past, you might feel that difference in weather conditions, and it's related to pressure. We'll get into that more in class. The air pressure at sea level is about 1 kilogram per centimeter square. So we will translate that into a value that deals with millibars. And that's where we talk about our 1,013 millibars over time in class. What we worked with in partial pressure was 1,000 millibars. And we mentioned that we fudged that number. The reason why was for discussion and arithmetic purposes, so that we could have a nice even number to calculate values from. But we're at the point now where we need to understand a greater detail and a more accurate value in millibars of the pressure when it's normal at sea level. And that is the value here in front of you. It is a 1,013 millibar. And that's one of the things that we do need to work on putting into memory. So this is a pretty important value, not just 1,000, but 1,013.25 millibars. 1 millibar is equal to 100 newtons per square meter. And those of you that's had physics before, that's something that we refer to as far as calibration of a similar concept there. We won't get into the newtons of pressure. Our focus will be right here. So what we'll look at the most is 1,013.25 millibars. And if you can commit the 1,013 to memory, that will be outstanding for our purpose here. That 0.25 we'll work on maybe a little bit later. But right now, let's just take our 1,000 and improve that to 1,013. The mercury barometer, remember, a barometer is what measures atmospheric pressure. The mercury barometer Remember our stage of instrumentation based on history? That was developed by an individual with a last name that hopefully you can recall, started the letter T, Torricelli. We said he had a dish that was open and it had a container that collected mercury, or that had mercury inside of it. And then we said he had a glass straw. And do you remember what was driven up into that straw from the dish? We had mercury driven up into there when we had a higher or lower pressure day. Well, if we have a greater amount of pressure pushing down upon that open container of mercury, causing the mercury level to go higher, then it must be a higher pressure day. And that's kind of what started our first attempt of calibration of pressure in the atmosphere. So we do need to make that link, and that goes way back to week 1. And so while we're further along than that in the course, that is a connection that I'd like you to make as we progress through this chapter. So what happened is the air pressure pushes on that pool of mercury, and that pool of mercury is what is in here. So this material is supposed to be that pool of mercury, and that's what we need to connect to. And what we found with observations over time is what we discussed in class. High pressure, the mercury goes further up the tube, and low pressure, the mercury stays lower. So here's a little more formal sense and a little higher understanding of what's going on. First of all, we need to introduce a vacuum into this. It wasn't just a regular straw, it was a vacuum. And a vacuum is an atmosphere that has no pressure in it. We've removed all of that outside of it. And that allows us to have the free negotiation of the height of that mercury within it. So most of you seem to have a very good concept of this air pressure pushing down and the mercury in the container. We just don't use the mercury in this open sense anymore. We use a similar fashion in a lot of other electrical based barometers, and we can get information from that as well. So this is what set us up for our average sea level pressure. We noticed over time that we had about 29.9 inches of mercury, which was equivalent to about 1,013.25 units of millibar. And that's when things are normal. But do look at our bumpers here. These are going to be important. We're going to work on these a little bit later in the course, but do start to work on committing some of these thresholds to memory. If we have a strong low pressure system right here, if this is a strong low pressure system, we're going to get down here to about 985 millibars. Okay, that's something that would probably put us into a thunderstorm warning or something tornadic in the atmosphere. When we get to something cataclysmic like Hurricane Katrina, we are getting close to the bottom of what this planet's threshold can be. Our lowest recorded sea level pressure is 870. So at the time of this recording and this PowerPoint, our record is about 870. And that is where we see Typhoon Tip way back in 1979. So as far as our lowest atmospheric pressure on this planet, we're going to recognize that as 870. Now let's go to the top of this scale. If we go further into the atmosphere and further at a deeper point into the atmosphere, what we're talking about in Siberia is a 1,084. So we're at about 1,080 millibars for our upper limit. This is about the upper limit of what this planet can withstand. And down here is our lower limit. So these are our bumpers planetarily on this world. So anything in here in the middle of that is fair game. When everything is normal, we're about right here. This is when nothing unusual is happening. And as we drop further, then we're becoming more inclement. When we get to this level, we typically have thunderstorms, and the intensity of those thunderstorms will become more and more and more aggressive as our mercury drops. Those are things that we see. After the thunderstorms pass, we have a return to normalcy, and then our pressure typically drives up as things become significantly improved in comparison to that of a significant thunderstorm. So that's where we see an anticyclone, which we'll talk more about in the course. So we can use mercury and a barometer to really help us get a snapshot of what the atmosphere is doing, has done, and will do over a certain short period amount of time. It's a very important tool, which is why it'll be mentioned a lot through this chapter and course. Pressure changes with altitude. Hopefully you can remember this from the past. Air pressure decreases with altitude, and we do have to talk about gravity with that, and we do have an increase in depth in the atmosphere. So we're talking about moving lower into the lower atmosphere. So at sea level, or we could even be below sea level in some very arid regions of this world. So what we're looking at here is the continuous collision of gas molecules as a definition of air pressure. So when we have more gas molecules packed closer together because we have a greater force of gravity, because we're deeper in the atmosphere, because we're closer to the surface of the Earth, then we have a system that works. So imagine this being the circle of the Earth, not very well drawn, but overall, gravity wants to pull you right toward the center of that. So when we have things like gas molecules that are really close to the surface of the Earth, we're going to have a higher level of pressure than we are when we're at the top of the atmosphere or troposphere in this discussion. If there's an area that can be slightly below sea level, which would be kind of weird, but we do have those locations, then we would have even higher level there. So gravity is at the driver of that. So here's a diagrammatic sequence that takes place in air whenever we change temperature. So we do know that temperature is a major influence factor of air pressure. When we have cold, more dense air, notice the distribution of molecules of cold air. They are closer together because there is less kinetic energy. Therefore, we are packing them in a tighter configuration, causing air pressure to be higher or lower. Well, because we're having a slightly different type of a situation there, then we would have a entirely different situation as far as pressure. When we have molecules that are farther apart like this, then that's where we're going to have a change in pressure as well. So we can see these types of densities that do sometimes play out. Now, what gets a little confusing is if you look, even though we have an increase and decrease in temperature, it does influence the air pressure, but sometimes it's not of a great consequence. So we do see warm air and we do see cool air being a driver of this, but not nearly as important as that of altitude. But temperature is important. So can you tell me which one would be the greatest air pressure if we drove these into an extreme environment? Do you remember from our last slide? Remember when we got to Siberia and we looked at this, Siberia was a very cold area. We're looking at that even in the winter months, and then that's where we saw these types of situations where we had higher pressure. So if that's true, then this must be a higher pressure when we have colder air, and then we have warmer pressure, warmer temperatures, which must mean lower atmospheric pressures. And that kind of gets us to a little bit of a understanding. Water vapor affects air pressure as well. If we pack more water vapor into a sample of air or into an air mass, we're going to drive those pressures up. If we remove water vapor, we're going to, of course, reduce those temperatures, which is partially why we have cold, dry air with higher pressure. So when we have cold, drier air with higher pressure, we have the ability for those molecules to be able to pack together. When we have warm, dry air, it has a higher pressure than equally warm, moist air. Remember, those moisture material, those moisture components, that water vapor specifically, needs room. And if it squeezes that in there together, then what we're going to see is, because we have more bulky water vapor inside a parcel of air, it's going to have a lowering pressure environment. So we're kind of splitting hairs here a little bit. We're at this point that we need to recognize that we have the influence of temperature and the influence of moisture. However, we have the idea that we need to understand dry, which is less than humid air, and then we need to have moist air, which is saturated air. And when we have those two, we have a slightly different configuration of our pressure changes that take place. And we'll get into these more later, and we'll practice with them in class. The motion of air, we can definitely have this that impacts pressure. Convergence occurs when net inflow causes pressure to rise, so we're jamming more molecules in there, and that can cause an inflow of pressure because of a mass migration of those molecules. Divergence, when there's no major inflow into that equals the amount of outflow, we're going to have a drop of that. So divergence might be likened to a balloon that has no air being put into it and it has a slow leak out. Convergence might be where we have air that's being put into a balloon at a faster rate than the air is leaking out. So even though a balloon might have a little bitty tiny hole in it, maybe something that's along the size of the tip of a pin, then if we have the nozzle opening that's taking air in, even though it has a hole in it, we could have a convergence process that drives air pressure up into that balloon. So those are things that hopefully kind of make sense, and we'll reinforce that with discussions in class as well. Three things that affect wind informal: pressure gradient force. We will refer to this as a PGF. Pressure gradient force will be something we refer to in labs and class as a PGF. We'll do a little bit of calculation with that. Hopefully you've heard of Coriolis force. This is something that those of you with a physics background have worked on before. And then friction or drag is something that we so often talk about in automotive circles, especially in high performance and definitely in aviation. Pressure gradient force is a process where we have the net flow from high pressure, and then it moves into a low pressure force. And the reason why it moves from high pressure to low pressure is the same reason of the past two slides that we saw with the density configuration, those molecules. The more dense they are, the more likely they are to flow out of that region. This is overpopulating a balloon with air. It's going to pop. This is opening up a door in a certain season to a house that is heated or cooled. We have a flow of that, and we feel these in certain types of environments. If isobars, and remember isobars, iso lines are things that connect areas of equal value. We talked about isotherms as temperature. Now we're talking about isobars, which is kind of like barometric pressure. And these are isobars that we're looking at. So if isobars connect areas of equal pressure and they're close together like they are in this region, then we're going to recognize this as a steep pressure gradient, meaning atmospherically we've got high winds. If we look at the disparity here and we have a very significant distance between our isobars, that means that we have light winds in this region. So we would expect this geography to have light winds, and we would expect this geography with the larger asterisk to have a much more significant wind field. That's the pressure gradient that we're looking at. So those are things that will help us meteorologically determine what is or is not in a certain region from the wind that takes place. Here's a couple diagrammatic examples. Sometimes this gets a little confusing, but this wraps up a little bit about local winds that sometimes throws us off a bit when we look at the altitude. So let's make sure we got what's going on. We know, hopefully, that high and low pressure feed one another. So that being said, high pressure at the surface will flow to low pressure at the surface. Low pressure has air that is lifting, and that is because we have a heat source here, the sun, that's causing air to be less dense. Remember those molecules 3 slides ago? Those are able to rise up here. They're able to heat up, greater kinetic energy. Well, when they get to the top of the atmosphere, we're going to have high pressure build up. They're eventually going to kind of stop and not entirely stop, but slow down. When they do, they're going to congregate in this area. And then we're going to have a high pressure system. That means high pressure aloft must flow to low pressure aloft that's above high pressure at the surface. So here's what's a little confusing. This is all aloft. We're talking about this in a different part of the atmosphere than down here. You live at point B, down at the bottom. So when we have high pressure, we could have low pressure aloft. When we have low pressure at the surface, we could have high pressure aloft. And this creates this convective cell that we'll talk about in class. And this drives these types of local winds. And one of the ones we'll talk about in regards to something like this is land breeze and sea breeze. And this is what these slides are depicting. So when we have ocean and we have a land mass over here, what we get into is land heating up in this position here at point A. Land heats up faster during the day than it does, than water does during the day. At night, water, remember specific heat, is going to hang on to that heat more, and we're going to have a change. So when we have the situation where high pressure is moving to low pressure, because the land is warmer than the water, high pressure will flow toward low pressure, meaning we're going to have a sea breeze during the mid-afternoon after the land heats up. We're going to reverse that flow at night. We're going to reverse that flow because what will happen is over water, we will now have low pressure. So at night, we will have a low pressure environment over water, and then therefore, we're going to reverse our flow of air from over land to the water, making a land breeze at night. What we're looking at in those charts are pressure centers or pressure systems, and they are very classic. You've seen them a lot. We have a low and we have a high. We need to connect terms to these at this point. We need to call high pressure systems anticyclones or anticyclones, and we need to call low pressure systems cyclones. And the ones that we'll talk about the most in this course is mid-latitude cyclone. And this is a term that we will use because of our location at 38 degrees north. And this is the one that will affect you most in your life as long as you live at this position. So mid-latitude cyclones are low pressure. Anticyclones are high pressure. Here's your broad connection now. Anticyclones are areas where we have clearing conditions. Therefore, mid-latitude cyclones must be rainy or inclement. Here's an example of one of those two. This is going back to 2013. A pretty significant storm. But check out the flow. Do you see how we're spinning in this direction? We have dry air in this area. People in this region are loving life that were in the southern tier of the Midwest. We can see our southern tier of the United States there. It's below the Great Lakes. And then the Great Lake Basin is experiencing some pretty aggressive weather. Now, because of those arrows, hopefully you can see that spin that is counterclockwise. Now, is that a low pressure or high pressure? Definitely low pressure. Is it called cyclone or anticyclone? Because it's low pressure, we're going to call it a cyclone. Now, where is it located? In the mid-latitudes, meaning this is called a mid-latitude cyclone that we see swirling around. And it's not the only cyclonic pattern that you can see in this vapor trail. It's pretty amazing. We've got a disturbance here that's taking place. You got a disturbance here that's taking place. So it shows this edification of air, of moisture, of turbulence in the atmosphere. And this is part of the reason why forecasting is difficult. Now, what did this change into? Well, check it out. This is our regional forecast radar that took place. And again, this is 2013, and this is certainly precipitation. One of the things that's interesting about this is to look at the linear fashions of precipitations that's taking place across Tennessee. Look how organized these are. They're almost in direct lines. And a big reason why that is because this area was receiving what type of temperatures? Do you remember if this region was cool? This is warm. And so this was an area that was uncharacteristically warm. And these guys, as this air was wrapping around, these guys were getting a significant amount of precipitation. This is what fell out of that. We had a pretty significant storm. And what we had was air moving in like this. And as it moved in like that, really no big concerns in this region. They actually had a pretty amazing day, pretty amazing time period there. As air went up here and got cool and circulated down, it grabbed some moisture from ocean waters, from evaporation, those qualities there. And as that happened, we created a pretty significant snow generation in this area. What was Florida receiving? Thunderstorms, aggressive thunderstorms, as we had a significant difference between land temperatures and ocean temperatures when we looked at that. So this was back in the February, later February of 2013, and this is a pretty significant storm that was moving through, and it was a classic example of what we're talking about here. Now, moving on to the Coriolis force. This is where we have a modification of the wind flow. It doesn't generate wind, it just modifies it. It is a deviation to the right, an alteration, a change to the right in the northern hemisphere. So work on remembering northern hemisphere, the Coriolis force modifies the wind to the right in the northern hemisphere. In the southern hemisphere, it's the opposite. So the Coriolis force affects the southern hemisphere. Whenever it does affect airflow in the southern hemisphere, it will make it deviate to the left. It is a deflecting force that is not generating wind, and it's always going to be directed at right angles in the direction of airflow. That doesn't mean the air turns in a right angle or deflects at a right angle. It's just going to be imparted upon that. It will control only the wind direction. It doesn't cause the wind to speed up and slow down. And it is affected by wind speed. We do see a factor there that does result in a different force whenever we have a greater amount of wind speed. It is the strongest at the poles, and we see it being non-existent at the equator. And we'll look at a slide that will hopefully reinforce that. So let's consider this. We have a target that is at the equator, And let's consider we have a non-rotating Earth. If I have something like an aircraft that I want to fly from the North Pole on a planet that is not moving, all I've got to do is chart my course and fly a certain meridian or a certain line of longitude south toward the equator, right over North America, crossing close to the Michigan Basin there, and I hit my point exactly. But that's not real world, because you know that this planet spins. It spins counterclockwise as we view it from the North Pole. So that being the case, what I have to do if I want to hit my target is I've got to change. I cannot just travel a straight line to get to my target. What I have to do is modify that a little bit. And pilots sometimes have to do this depending on how they're traveling. So what if we didn't? What if we just talked about this with a non-mechanized flight and said we had an air mass that's moving from here and it's moving south? It will be deflected to the right. And as I look at this, it looks like it's deflected to the left. But remember, I'm traveling from the North Pole. So put yourself at the North Pole and walk south. That means that our deflection would be to the right, as our planet had a rotation in a counterclockwise fashion. And that's in the northern hemisphere. So what we say is the Coriolis force deflects free moving objects to the right in the northern hemisphere. And that's what this exemplifies. It gets a little confusing. Use this as a resource tool to it. And then whenever we get into our lab and we focus on this, we'll have 2 points of contact in class. Ask those questions. This is something that sometimes is a little challenging. Friction is another thing that deals with the disturbance or deflection of wind. Airflow aloft is typically unaffected by much friction. There's not too much there. We don't have the density of molecular mass present, so it's able to flow around. So our jet stream is able to really clip along at a pretty good rate. However, when we get next to the Earth's surface, and this Earth's surface looks a bit odd, but what we're looking at here is snow and kind of an alpine condition where we have maybe coniferous trees there, maybe something like the spruce. And as that happens, we're getting a lot of change in this part of the atmosphere. And that's because of friction. So friction does influence airflow, and it causes it to be a little bit turbulent in some situations. Weird names are introduced during this part of the discussion. We have things called geostropic flow. This is when we have a pressure gradient force and a Coriolis force being balanced. This means that wind flows parallel to isobars. Okay, so when you look at these weather maps, the ones that are scattered throughout this chapter, the ones that are scattered out through our labs, when we have airflow and it's parallel to isobars, it is going to be called geostropic. They flow in relatively straight paths. So that gives us a geostropic flow. So think of things that are in the upper atmosphere, and it's not very real world to us beings that live down into the lower troposphere. But that's what we're talking about with geostrophic flow there. We will work on that in lab and kind of get a better concepts. A neat law is produced by this statement, and that is Bayes-Ballot law. And what we're talking about is standing with the wind at my back. So there I am standing, the wind is striking my back. And if I have my right hand up, then high pressure is going to be on my right-hand side. On my left-hand side, I'm going to have low pressure. That sounds kind of odd, but check this out. So say that I'm in a airflow that's like this, and here's a gradient wind. And what we can see here is if I'm standing in a position that is, say, really close to Indiana in this map, and my back is facing to the west, and my eyes are facing in this direction. Let me try to draw this. So my eyes are facing east, and my back is facing west. To my right is high pressure. To my left, so I'm going to put a right up here. To my right is high pressure. To my left is low pressure. And that's Bayes-Ballot law. That's what we're getting into there. So when we state that, Bayes-Ballot law, high pressures to the right, low pressures to the left, that's what we're getting to. And again, I would be standing about in Indiana's location here, and I would be looking, my eyes would be facing to the east. Curved airflow aloft. This is where we get into gradient winds and different changes. We also introduced the concept of trough and ridge. And we've talked about these before just in the general analysis of our daily weather when we have significant changes. But do make sure we understand how we have gradient winds that are parallel to the curved isobars. So think kind of geostropic there. We have a counterclockwise flow of low pressure in the northern hemisphere. These are things that we've talked about in this bulleted item. And this brings us into a trough. This is the net result of isobars curving to form regions of low pressure. So let's go back here. Here's where we have a trough, low pressure, and we have a trough region where all this drawing is. So this would be determined in a trough. Why is it like that? Because we are associated with what type of pressure? Low. That's supposed to be an arrow right there. So you see that low pressure. Where we see a ridge being developed right here. Why is there a ridge there? Because it is associated with high pressure. So that's what we're talking about in regards to trough and ridge. And that is where we get into our connection of high pressure and clockwise rotation. And that's where we see those types of things being cyclonic and anticyclonic. Winds aloft. These are things that we will analyze in lab. We're going to go over them here to give you a reference point. These are things that we start to see a change of wind direction. It helps us predict where certain airflows will go. So when I have low pressure, remember PGF, our pressure gradient force? Our pressure gradient force is trying to move things into this system. So because low pressure is a counterclockwise circulation, it's going to be not only counterclockwise, but it's also going to be moving into the center across those isobars. And that is something that we do see that takes place at the surface particularly. But when we're at the surface, we're going to cross those isobars. When we are not at the surface and it is a gradient wind, then the airflow is going to stay in these lanes. And these lanes are determined by isobars. So two things I want you to understand with this slide. I've kind of drawn them on top of one another. If these winds that are blue lines are staying in their lanes, they are a gradient force wind. They are not affected by things like friction at the surface. They are able to flow in a traditional fashion. If they are moving outside of that point and the pressure gradient force pulls them out and they continue to move outward, like for example, say this continues to move outward and move out like that, that's going to be at the surface. If the high pressure moves outward and then stays in the lane like this and it becomes balanced, if the pressure gradient force becomes balanced with the Coriolis force, which you see on these slides, then we are in a geostropic balance. So we got two things going on here, and that gets a little confusing. We'll reinforce this in class. But right now, if you can remember that at the surface, we have winds that are crossing isobars, not directly, but they move out, move in, depending on if they're high and low pressure. But if we move aloft and we just have the balance between pressure gradient, the PGF, and the Coriolis force, then we're going to have that geostrophic balance. And that's what this is trying to show as well. So there's a lot of analysis in this chapter that might be a bit technical, depending on your background of physics and just chart interpretation. But here's where we're at the high pressure system. At the high pressure system in the northwest, we have an anticyclone. The air is spinning clockwise, and as it spins clockwise, it's subsidizing, it's sinking toward the ground. And as it spins in that fashion, it's going to break out of these isobars. And the reason why is because we have an out of balance like pressure system, mainly because of friction. It's able to pull that in a different way. Mid-latitude cyclone is in the area that's more eastern in the map, and we see this crossing. So whenever we see these two things, there's two analyses that need to take place. If I have winds that are crossing isobars and still moving toward the center of a low pressure, am I aloft or am I at the surface? I've got to be at the surface. How do I know if I'm aloft? Well, if I have a balance between the pressure gradient force and the Coriolis force, and the winds either went in toward the middle or went out from the middle and then stayed in their lane, then I must be aloft in the atmosphere. So let's talk about friction a little bit. Increased friction causes a drop in wind speed, and there we have a pile up. We've got to get into an inflow and an outflow type of process here. Convergence can result in cloudy weather, and then when we have decreased friction, where we're increasing is the wind speed, and that's where we have a change as well. So overall, friction has a tendency to adjust things a little bit, and we do need to bring these things in. They can be particularly noticeable from satellite and from radar whenever we have a island, and certain seasons during certain types of heating or cooling trends in the ocean environment allows us to have a condensation point built up, and we can see this type of buildup of swirling in the atmosphere because of these. Subsidence and divergence results. When we talk about subsidence and divergence, these are terms we need to work on understanding from a diagrammatic perspective. But we're either talking about moving apart or moving together there, and we'll work on those in our in-class discussions to reinforce that. But here's where they are. When we talk about subsidence, what we're talking about is air that is sinking. So think of air that is sinking, but not just in a straight line pattern. This is subsidence. So when we have subsidence and air is sinking, we're having pressure build up. Therefore, it's considered high pressure at the surface. And then when it hits that high, or when that high pressure builds up at the surface, it's going to diverge. And that air is going to diverge and spread out. This can actually feed into a converging surface wind. This is called converging because the air is flowing into it. Why is the air flowing into it? Because it's lower pressure, and like a straw, the material on the inside of this column is being pulled up. That creates a reduction of kinetic energy up here. So what we have is a lot of times a lifting condensation level. Remember our clouds being melt, and as our lifting condensation level is hit there, we have such a drop of kinetic energy that we actually build pressure, and then it's able to flow back into the most low pressure environment, which happens to be stacked above this high pressure. And then we have that flow. So we're bringing kind of everything into here. We got our counterclockwise circulation, which is called a cyclone above the low pressure. So this would be our cyclonic fashion. And then we have at the surface, our cyclonic fashion at the surface. And then this is where we have our anticyclonic type of nature at the surface there. So a lot we're bringing in here. We will practice with these things in class, but this is throwing together a lot of material so far. Wind direction and measurement here. Prevailing winds are what we talk about in large bulks. Across this latitude, you guys are located at 38 degrees, most of you, and we have a prevailing wind that is prevailing from a direction that you should know. If you don't, it's from the west, it moves to the east, and that's why we have most of our severe weather that moves in from the west, southwest, or northwest, depending on what season and what trend is necessary there. A comment about wind. Remember, wind direction is always measured from the direction it is moving from, or where it is originating. Therefore, a north wind moves from the north to the south. So if I drew a north wind, I would say a north wind is moving north like this, but it's originating from the south, but I'm calling it a north wind. And then whenever we have those types of things, then we have, and I stated that wrong, so let me retract that. Whenever I drew a wind like this would be a south wind. A south wind is originating from the south as it moves to the north. If I was making a north wind, if I drew a north wind, I'm going to go here to the left of this comment. This is a north wind. The north wind is originating from the north. So because the north is up here, then this is a north wind. A north wind is moving from the north to the south. So just for clarification, at point A here, this is a south wind. I stated this wrong earlier. A south wind originates in the south and it moves to the north. This at point B would be a north wind, and that's where we see that direction being originated in the north, moving to the south. And if it stayed like that over a significant period of time, we're going to call those winds prevailing. So here's where we see measuring and being brought into play. Here's a southeast wind. The southeast wind is originating from the southeast, and it is moving in that direction where it's moving toward the northwest. And we can use these, and this is fairly intuitive. Anytime you see these lines like this, that tells that there's an intensification of that wind field. Wind vane, you've seen these before. Think of barns. These are things that typically are put on top of a structure that's called a cupola, on top of barns. Very customary in the Midwest, and a lot of times they might be accompanied by a rooster, maybe a tractor, maybe a horse, something like that, maybe a family crest on top of that, not a crest, but a family set of initials on top of those. And a wind vane is going to be that north, south, east, west arrow type of depiction. It tells us how the wind is moving. A cup anemometer is something that we'll display in class. We won't work on these. These have been changed around. We now have turbine anemometers, and they work a bit more detailed, and they're certainly more convenient because they're pocket style. A cup anemometer has these, as it sounds like, cups or hemispherical style cups. Think of taking a tennis ball and cutting it in half. Those things capture the wind, they move around. So we'll display what one of those look like in the classroom, but we won't work with those. And then the turbine is what's replacing those. An aero vane is taking an air vane and anemometer, kind of putting that together, and that's a pretty handy device when we look at those. That'll do it for chapter 6. Thanks for tuning in. This is probably got more content than we've been seeing in some past chapters. So I would encourage you to read this and sections of it more than once, to use this broadcast as something to help you understand these types of concepts, and certainly pay attention to those labs. Chapter 6 is building content together, and it's not that any one content is more significant than the other. It's just that we're layering the content at this point in the course, and we've got to have a building process to understand future processes. And eventually we'll get into the forecasting, and we got to tie all these things together. So keep up the good work, and if you have any questions, let me know. I'll answer those in class, or at the individual level. But anything that's confusing, ask. I'll see you in class.